Hey, hello. So, welcome to this SystemVerilog Operators session, and this session is going to be more of a refresher because I think the many of the operators either you would be familiar from other programming languages or from the Verilog. What I'm going to do is I'm going to go through this session very quick and emphasize only the few key points rather than explaining each of the operator, and thereon if you have specific questions about any operator you can reach out to me. So our agenda today will be like we'll look at what are the overall operators that are supported. We'll look at the arithmetic operators, then the equality operators, then the logical operators, then bitwise operators. Then we will look at the shift operators, concatenation operator. This might be something new for you guys. Replication operator is something new. We'll spend some time over here. Set membership operator, we will spend some time here as to what it means, and then the streaming operator. So the last four we will spend some time. For the rest of them, I think most of you are aware. I'm going to emphasize few key points that could be potentially useful. But other than that, I think it's just a regular things that you are mostly familiar with. So let's start with the like overall scheme of operators. So we have assignment operators, and there are different flavors. The simple blocking assignment we are already aware, and then you have this plus equal to, which is equivalent to a of I equal to a of I plus 2. This is a shorthand notation, and this type of shorthand is available for plus, minus, multiplication, division, modulo. So most of even for the shift. So if you want to operate on the same element, then you have this shorthand notation that you can utilize. And then you have this conditional expression operator, which is also called as like a tertiary or a ternary operator. So you look for a condition, and then if it is true you execute this expression, if it is false you execute this expression. Then there are a bunch of unary operators, so these are also very useful. Unary, some of these operators, among them few of them are also called as reduction operators. We will look at them. So you can take a single vector and operate on them, right? Like if you have a vector and you want to or all the bits in that particular vector, or and all the bits in that particular vector, sort of similar to what we looked at the array reduction methods. If you remember, in the aggregate arrays we looked at the array reduction methods. So they are something similar, but those we were operating on unpacked arrays. These will operate on packed arrays. Packed arrays meaning basically your bit vectors. And then you have a bunch of binary operators which will operate on two numbers. I mean, like we have addition, subtraction, multiplication, division, modulo, equality. So we'll look at it very quickly. Then you have a C style increment or decrement operator, plus, plus and minus. And then you have streaming operator, which is new. With respect to this increment and decrement operator, what you need to remember is if you are using this type of a notation when you are doing looping, it doesn't make any difference. But while you are doing it in the some sort of an assignment or an operation that will use the value after the inside an expression, if you are using the plus plus or minus minus, you have to be aware that whether you want the particular value to increment after usage or you want it to increment before usage. So this aspect you need to take into consideration. Like let's say I am keeping an static variable and I want to use that static variable as ID for every time I knew a class. Then and if I want my ID to start from 1, okay, so I've initialized it to 0 but I want it to start from 1, then every time I want to stamp it I will do it with plus plus I. So the first class gets created, I will say plus plus I, so that the value 1 gets assigned as an ID. So that is the way you have to be aware that how the pre or post increment operator should be utilized. So here we have arithmetic operators. I'm not going to talk much about this first four operators. You are mostly aware of it. This modulo operator is useful. So sometimes while you are doing some developing some constraints or something, then mod 2 being equal to 0, right? The mod operator applied with this specific number 2. So mod 2 being equal to 0 determines that number is even, and mod 2 if the remainder is 1, then it means odd. So to set up the constraints to generate even or odd numbers, the modulo operators are very helpful. And the exponent type of an operator is also helpful for the parameterization of your design. Like for example, I could say the total word width is 32, half is width divided by 2, which is 16. And if I want to extract, let's say, the only the half of the word from a 32-bit, I want to generate a mask for it, then I can say 2 exponential of half width minus 1. So what this will give me is, it will give me the lower 16 bits as all ones, right? So I will get like 32 hex, then the upper 8 nibbles will be 0 and lower 8 nibbles will be F. So that is what I can generate by using this type of parameterized approach. And during that point, this exponent operator is useful. So that is something that to make a note, that the modulo and the exponent you want to remember, because this is something that we generally don't use it very often, but yeah, these operators are useful for solving some tricky problems that you might encounter. Um, so equality operators, I think we have these 4 of them. We have like a case equality. So if you notice over here, this equality has 2 equals to, but this one has 3. And similarly, this not equal to is single, exclamation mark and equal to, whereas it's a single exclamation mark coupled with 2 equals to. So okay, this is a case equality. We have the concept. The top 2 are case equality and the bottom 2 are the general equality operators. So the case equality, what it does is, it takes into consideration the it will also compare the both the values when the x and z are present as a part of the values. But if we use a non-case equality when the x or z are present, then the result could become an unknown value x, and when you check unknown value x in some if, it will always appear as a false. So that is something that you need to be aware of, that if you are doing some interface level signal sampling and you are trying to compare that with something, then you should always rely on case equality operator, so that the exact match can be obtained. And but if you are doing it at the higher layers in the test bench, then the general equality itself is sufficient. So when you are doing in the driver, when you are checking, if you want to take some action, if the value is x and z, then you want to rely on case equality. But sometimes it may so happen that there could be x or z's. Let's say 4 bits are there, out of that 2 bits can be some x or z's, but other 2 bits is what you really care for. Then you have this another operator called wildcard equality. So in the wildcard equality, what happens is, just note the way it changes. So it's double equal to with a question mark and bang equal to with a question mark. So wildcard equality. So in the wildcard equality, if the right hand side operand contains any x or z's, that will be treated as wildcard. So that it won't be sort of matched with the matched, or it won't be matched, or you can consider it as it will match with whatever the value that is contained in the left hand side operator. So I have sampled some value, I want to compare it, but I want to compare only the bits that have the legal value. So in those cases, I can use the wildcard equality operator, and it will ignore the x and z's, and it will compare the still legal value. So if I got, let's say, I am comparing let's say 1111 4-bit value, I am comparing wildcard equality with the 11ZZ. If the value is 11ZZ, it will still match. It will ignore those Z. It will be treated as wildcard. It will match to either 11 on the other side. So that is the wildcard equality. But if the left hand side operator itself contains x or z, so what we talked about is ignoring happens for the right hand side operator. But if the left hand side operand itself contains x and z's, then the result will, and then it can result in x again, as we saw in the case of the equality, the general equality operators. The same results will show up even with the wildcard equality operators. So then we have the logical operators. So logical and logical or, you guys are aware. So you have any expression that results in a Boolean value of 1 or 0, then you can use logical and to combine them to generate a combined expression value that I can say x equal to 1 and x greater than 4. Like for example, we saw that type of an expression in case of array locator methods, right? So you remember that. So there you can use the logical and the logical OR operators, multiple expressions which result a Boolean value. You can combine them. And you have this logical implication and logical equivalent that I have not really used ever, but what you need to remember about it is that this logical implication is a shorthand for this particular expression, that is not of expression 1. So if I said expression 1 with implication operator expression 2, that is equivalent to not of expression 1 and the logical OR of expression 2. So if ever you come up with an use case where you have to do this type of an expression, instead of writing it in this format, you can just write it as expression 1 with implication operator of expression 2, and this is how the truth table behaves. Anytime a is 0, so if I did a implication of b, since a is 0 over here, this value will become 1. A is 0, the value will become 1 irrespective of value of b, because it's a logical OR over here. And then with a value of 1 but a b value of 0, so the overall result will be 0. Then a of 1 and 1, it will still become 1. Okay, so here we have the bitwise operator. So bitwise operators will perform operation on two vectors that you can specify. So it will perform the specified operation on the individual bits and provide the resulting vector. So you can perform bitwise AND, bitwise OR, bitwise exclusive, or exclusive NOR can be done by combining unary negation and the exclusive OR. So it's expressed this way. Both of them are valid. So you can do unary negation, and then bitwise NAND you can do. Then you have the bitwise NOR also can be performed by combining the unary negation with the OR, and so these are the bitwise OR operators available. And then we have this bunch of reduction operators that we talked about. So the way reduction operators are different from bitwise operators is the bitwise operators operate on two operands, whereas the reduction operators operate on a single operand. So I could just be saying and then followed by that I can specify a vector. So what happens is, if I specify a 4-bit vector, then all the bits within that 4-bit vector will be ANDed with each other, and then it will give the result. Similarly, you can do, that's why they are called as reduction, not the bitwise. So you can do reduction OR. So I can specify this OR operator and then specify a vector, and then all the bits present within that particular vector will be all together. So some of the examples are shown over here, and the way to look at it is sometimes each of them specify, like you can look at it like, for example, when no bits are set, right? So you can see that NAND is 1, okay, and NOR is 1. So if you have to detect no bits set, then you can use these operands, right? And then all bits set. So of course we know that the AND is the one. Then if the even bits are set, that's something like here both the, I think the NAND is also giving a result of 1, and then but to specifically detect it, you have to use the XNOR, and odd bit set you have to use the XOR. So this even and odd bits set check is something that you can rely on XOR and XNOR. Even with XNOR and odd with XOR, this is also sometimes useful for you even during the problem solving session. So you will have to remember them, and if the X and Z's are present, then this is how the resulting operations comes out to be. That is like, if it is a 1 and then you have an unknown, then it will become unknown, then 0 and unknown will become 0. So it works on the basis of this truth table. Then you have the shift operators. So I think you have logical shift right and left, and then we have arithmetic shift left and right. The one extra of those arrow symbols in the arithmetic shift. So what you have to remember is the power of 2 number generation. The shift operators are useful. For example, I can start with 1, and if I keep shifting left, it will always generate a number which is power of 2. So first it will when you take this number 1, and then if I shift it with 2 bits, then it will become 4. If I shift it with 1, it will become 2, 4, then it will become 8 if I shift it by 3 bits. So that way it will always generate a power of 2 numbers. So you can take 1 and shift left by any of the numbers, and then it will generate always power of 2 numbers. So it's something that you want to remember. And then shift left is same as multiply by 2. Okay, so and then shift right is same as divide by 2. This is also another rule that you want to remember. And then when you do arithmetic shift, the signed bit is what gets extended to the bits that are emptied out. That is another thing that you can remember. So that's it about the shift operators. And then we have this conditional operator, wherein what you can do is you can check for an expression, and if the expression is true, the resulting expression that needs to be assigned can be specified over here, colon, then the expression that should be assigned if the condition that we are checking is false. You can do it this way. This example, if you remember, this is the way we drive the bidirectional buses. If it is drive, then you say send out the data. If it is not, then you assign the high impedance so that you can read the bus of A somewhere else as an input and use it. So this is how you can use it as the in-out. That's the this question mark and the colon is the conditional operator. Then we have this concatenation operator, which is new in the SystemVerilog. I think so. The concatenation, what it does is it results, it joins the bits, okay, from one or more expressions. So I can say A and B of 30 W. All of these, the vectors are joined together, and the result will be the total number of bits that we have, and they will be ordered in this particular position. So the concatenation operator can be used either on the left hand side or on the right hand side, both. So here, for example, I am using it on the left hand side. So I have 3 different variables of logic, and I am assigning 3 tick B1 1. So each one of them are going to get the value 1. So this is also sometimes very useful. It is very useful even while you are doing the string concatenation. So it's curly braces, and then the list of values that needs to be concatenated are specified with the comma separated list. So then all of those gets concatenated. That's the concatenation operator for you. And then we have the replication operator. So a replication operator is also called as multiple concatenation operator. So it should have a non-negative number. Then it is done through this double curly braces. So if I have W and I put a 4, then yields 4 W's. So is equivalent to this. And then I can also have a pair of numbers, and if I do 3 times that, so you can see that AB gets repeated 3 number of times. So this replication operator is sometimes useful in with the parameters. So for example, I have a parameter of value of 32, and I want to create like a 32 tick ones, right? So that is all 8 nibbles of F. I can do that with the replication operator. So I'm using that constant over here, and I'm specifying 1 tick B1. Now this will become like a 32 tick hex, all 8 Fs. So that is what this will become. So that is how the replication operator is useful. Then you have set membership operator. So set membership operator is very useful in constraints. So something that you want to pay attention. So here what it does is, if you have an expression, it checks that if the particular expression is present in a list of unpacked array, and if it is present it returns 1, and if it is not present it returns 0. And the way it's performed is you check if expression inside, and you specified an unpacked array over here. That's how this works. So here I have specified an unpacked integer array, and I'm checking if that particular expression is present inside the array. And here of course I have also done the concatenation, and that also works. You can use like while val inside, and I'm using the wildcard character over here. Wildcard character can be replaced depending on the operand type, either with 1, 0, X or Z. So you can see that it matches all of them if you use this wildcard question mark in the bit vectors. Then you can also specify the values in the form of two, like a different range operator. So here what this means is, if the A is inside between 16 to 23, either it could be 16, 17, so on, then 21, 22, 23, any one of the values, then the A inside this will come out true. Then 32 to 47, similarly 32, 33, so on and so forth, 45, 46, 47. So all those values you can specify using the range operator. This is very useful. So this inside will find lot of application when we do the constraints. So yeah, if no match is found, then if some of the comparison results in X, then the result it will return is a X. So that is something that you maybe want to be aware of it. Then actually here I have not shown, but the queues and dynamic arrays can also be used on the like here we have used the queue, but you can also use the dynamic arrays on the right hand side. So I can check example inside some dynamic array, or expression inside some queue. I can do that. So I can put the queue or the dynamic array, and that use case is very useful. As I called out in the constraints, it's very helpful. Then this is the new operator called streaming operator. So streaming operators has a lot more than what I am showing over here. This is the special use case operator. So I'm showing you like one flavor of it, that how the streaming operators are useful. So streaming operators are mainly meant for, this is one thing that I want you to remember, that is meant for packing and unpacking. Okay, so packing and unpacking of the data in for the different formats. For example, let's say I have this byte array, okay, and I have these 4 bytes, right? This 8C00A4FF. I want to pack them into a single integer, okay, of 32 bits. Then this will become 8C004A4FF, right? So how do I do this? For this, I can use the right shift streaming operator. So here I have an example. So I have declared an array of 4 bytes, and then I've done the static initialization with the stick, and then I'm saying if I want to create a packed value, I am saying this double curly braces, as we have done for the replication operator. The difference over here is, instead of constant, I'm now specifying a logical shift operator. So that's the streaming operator. So once I do this, the resulting value will be the packed. So the right shift streaming operator will pack different units into a single unit, whereas the left shift streaming operator will do the unpacking. For example, I now have this 24-bit vector over here, 060708. I want to distribute it into these bytes A, B, C. So what I am doing is, I am using the left shift streaming operator, and I am saying byte A, B, C, and once I do this, then it will assign A with the value of 8, and B with the value of 7, and C with the value of 6. So left shift does unpacking and right shift does packing. This is what is the key concept behind the streaming operators. However, the streaming operators have many more special applications, which we are not discussing all of them. One more interesting case is that if I want to reverse the bits in a byte, I can use the left shift operator. So I have a value A, which is 8C, and then I am doing left shift of this value. So it will reverse this particular value and assign it to the value B. So it's unpack, and while in the process of unpack, it reverse the value. So this is what is the the application for the streaming operators. As and when I think you have more requirements for the streaming operator usage, you should refer to LRM. This is a special use case operator that has special use cases. It is there, but they are very involved, so we are not covering all of them over here. But remember that the streaming operators are using for packed and unpacked, right shift for packing, left shift for unpacking. That should be that concept. If you remember, I think the rest of it you can develop based on the need. So this concludes the quick session on operators. So we have emphasized some of the key characteristics from the information that we know. So thank you for listening.